So, today we will solve a few problems that we could not solve in my last lectures. So, I will solve one problem for axial flow machines. So, before I go to solve the problem on axial flow machines, I will briefly discuss about a few important features whenever fluid is flowing through an axial flow machines. So, I am writing problem which is very important on axial flow machine. So, if I draw the schematic of an axial flow machine again, so this is so this is the hub plus blades, that is impeller of an axial flow machines. Fluid is flowing in the axial direction and machine is rotating in this direction. And if I take a streamlines, so this is 2 and this point is 1, so 1 and 2. So, here streamlines are parallel to the axis of rotation, So, here streamlines are parallel axis rotation. So, before I go to solve the problem, here I will discuss that. Now, radius R1 equal to R2. So, hub and tip. So, radius R1 is equal to R2, therefore, the blade speed U1, blade speed at the inlet will be equal to blade speed U2 at the outlet. Since RPM is same, so pi dn by 60, pi dn by 60. Now, flow area at inlet, that is Q1, that is equal to pi by 4 into d hub square minus d tip square, d tip square minus d hub square, d tip diameter square minus d hub diameter square into Cz1, that is flow velocity at the inlet. Cz1 is the flow velocity at inlet. Similarly, flow area at the outlet, Q2, flow area at the outlet Q2 should be pi by 4 into dt square minus d hub square into Cz2. This Cz2 is the flow velocity at the outlet. Outlet means at the outlet diameter, at the outlet of the blade. So, now these two flow area we have obtained pi by 4 dt square minus dh square into Cz1 and pi by 4 into dt square into dh square minus Cz into Cz2. So, now flow area at the inlet, and outlet are equal. That means flow area at inlet and outlet are equal. That means it will give Cz1 is equal to Cz2. So, why? Because flow area at the inlet and outlet are equal, this will give Cz1 is equal to Cz2. This is from the continuity equation, because from continuity Q1 is equal to Q2 is equal to constant, right. So, from continuity Q1 is equal to Q2 is equal to constant. So, the flow area at the inlet and out, since flow area at the inlet and outlet are equal, because pi by 4 dt square minus dh square is equal to constant, from continuity Q1 is equal to Q2 is equal to constant. So, the flow, so this will imply that the flow velocity at the inlet and outlet has to be equal. So, that means if I go to the next slides, so the flow velocity, that means flow velocity at inlet and outlet will be equal, that is implying Cz1 equal to Cz2. So, this is the condition we get from the from this analysis. That means, if we talk about flow through and axial flow machines, then since the flow area at the inlet and outlet are constant, and from the continuity Q1 will be equal to Q2. So, it will imply that the flow velocity at the inlet and outlet has to be equal, that is Cz1 will be equal to Cz2. So, this is the condition, rather this is the conclusion what we get from this analysis. So, this will be important while you are solving a problem for the axial flow machines. Now, we will discuss one problem on axial flow machines, and that is what is very important. So, we will discuss one problem. I will write the problem. So, flow through rotor, of axial flow fan, right. The tip diameter of fan is 1.1 meter. Half diameter is equal to 0.8 meter. It is given operating speed, sorry, it will be axial flow pump. It is axial flow pump. The tip diameter of the pump is 1.1 meter, half diameter is given. Operating speed of the pump is equal to 1200 rpm. Absolute inlet angle is given 60 degree. Blade inlet angle is equal to given 30 degree. Blade outlet angle is equal to given 60 degree. Use mean diameter of the blade, rather using mean diameter of the blade, we have to calculate one, volume flow rate cube. Number 2, rotor torque. Number 3, absolute outlet angle. Number 4, power required. So, these 4 quantities we have to calculate based on the data given. So, we need to solve the problem. So, we will solve the problem. Now, we will solve that solution. So, volume flow rate Q1 will be equal to Q2. So, Q1 will be equal to Q2 is equal to let us say cube, whatever it is, will be equal to pi by 4 into d tip square minus d half square into Cz1 or Cz2 whatever we can calculate. So, now I am writing. So, this is the answer of question 1. Answer of question 2 is the rotor torque. T T will be equal to m dot into we know c theta 2 minus c theta 1 into r m, because it is given that we have to use the mean diameter. So, this is r m, so mean diameter. Okay, so r m is the mean radius, because it is given that we have to consider mean radius. So, this will be the rotor torque, and finally, if we calculate power, then power P will be torque into omega. So, that the answer of 4, that we will get Newton meter per second or watt, whatever will that will be, that we will obtain, that is the power. Now, we have to solve the problem by drawing the velocity triangle. So, now I am drawing the velocity triangles at the inlet and outlet. So, if it is an axial flow machines, axial flow pump, so this is the blade and this is outlet, this is inlet. If I draw the velocity triangles at the inlet and outlet, so this is C1 absolute velocity at the inlet, this is U1, this is W1, this is C1, and this is U2, this is W2, and this is C2. So, we have obtained, and this is the half diameter DH, and tip diameter will be like this. So, this is the tip diameter DT. So, we have obtained DT and DH. What is given? We have given flow angle, absolute flow angle alpha is equal to 60 degrees given, beta 1 is equal to given 30 degree, beta 2 is equal to given 60 degree. So, these are given. U is equal to U1 is equal to U2 is equal to pi d m n by 60, because we have to calculate, we have to consider mean diameter. So, pi dm by 60. So, mean diameter if we calculate, we will obtain pi into 0.95 into 1200 divided by 60, that is 59.7 meter per second. So, this is the blade speed. So, to obtain flow rate, we know dt, we know dh, only thing we need to know either Cz1 or Cz2. So, if we take the inlet velocity angle, so which one is the alpha? Alpha 1 is the 60 degree. So, this angle is 60 degree. So, from inlet velocity triangle, we obtain Cz1. So, this is the Cz1 and this is the Cz2. So, these are the Cz1 and Cz2 are the flow, flow velocity at the inlet and angle, flow velocity at the inlet and outlet. So, Cz1 divided by W theta 1 that equal to tan beta 1, beta 1 is equal to given, right. So, W theta 1 is equal to Cz1 cot beta 1. Similarly, we can obtain C theta 1 is equal to Cz1 cot alpha 1. This angle is beta 1 and this angle is alpha 1. So, from inlet velocity triangles we obtain W theta 1 is equal to Cz1 cot beta 1 and C theta 1 is equal to Cz1 cot alpha 1. So, what will be the total blade speed U? U will be equal to W theta 1 plus C theta 1, that is from the inlet velocity triangle, that is equal to Cz1 into cot beta 1 plus cot alpha 1, right. So, from here we can calculate Cz1 is equal to U divided by cot alpha 1 plus cot beta 1, and it will give a value of, because U is equal to 59.7, and if I put the value of cot alpha 1 and cot beta 1, cot 60 degree plus cot 30 degree, we will obtain the value of 25.9 meter per second. So, you obtain the flow velocity at the inlet is 25.9 meter per second. Knowing the value of this quantity, we can go to calculate Q1. So, flow rate cube will be equal to pi by 4 into d tip square minus d half square into Cz1. So, it will give a value that pi by 4 into 1.1 square minus 0.8 square into 25.9. So, it will give 11.6 meter cube per second. So, this is the answer for the flow rate. So, this is the answer for the flow rate we obtain. Now, we need to calculate another a few quantities, that is torque. To calculate torque, what we need to know? We need to know the value of C theta 2 and C theta 1, that is very important. So, how we can obtain C theta 2 and C theta 1? So, that means we need to know the value of C theta 2 and C theta 1, that is very important. So, W1, again if we look at the inlet velocity angle, again if we look the inlet velocity angle, from inlet velocity angle, what we can obtain? Cz1 by C1 is equal to sin 60. If we go back to the inlet velocity angle, so this is inlet velocity angle, this is C1, this is U1, this is W1, this angle alpha 1, this is beta 1, and this is Cz1. This is C theta 1 and this one is W theta 1. So, Cz1 by C1, Cz1 by C1 is equal to sin 60. From where we can calculate C1 is equal to how much? Cz1 by sin 60, that equal to 29.9 meter per second. So, we can obtain the absolute velocity at the inlet. So, now C theta 1, which is required to calculate torque, that will be equal to how much? That will be equal to C1 into cos alpha 1. So, C1 value we know 29.9 into cos 30 degree, and we will obtain this will be 15 meter per second. So, this will be 15 meter per second near about. So, that is what we obtain. So, we have obtained flow velocity, we obtain C theta 1, but now we have to calculate C theta 2. So, to obtain C theta 2, how we can obtain C theta 2? Because in that case we need to know Cz2. So, and C theta 2 also. So, Cz2 will be equal to Cz1, that equal to how much? That equal to 25.9 meter per second, that is Cz2. And if we draw the outlet velocity angle, so this is outlet velocity angle. So, this is outlet velocity angle, this is U2, this is C2, this is W2, this is alpha 2, this is beta 2, W theta 2 and C theta 2. So, from outlet velocity angle we can obtain that tan alpha 2 and this is Cz2, this one is Cz2. So, tan alpha 2 is equal to Cz2 divided by C theta 2, and C theta 2 will be equal to U2 minus W theta 2. So, we need to know, because U2 is equal to known. So, what we have to calculate? W theta 2. How can we calculate W theta 2? Because W theta 2 is equal to, again we have to calculate W theta 2. So, tan alpha 2 is equal to Cz2, C theta 2 is equal to U2 minus W theta 2. So, what will be W theta 2? W theta 2 is equal to, because again we know Cz2. So, W theta 2 by Cz2 is equal to cot beta 2, because we know beta 2. So, W theta 2 will be equal to Cz2 cot beta 2. We know Cz2, so we know U2. So, from if we calculate alpha tan alpha 2, we will because so tan alpha 2 is equal, alpha 2 is not given. If you go to my previous slide, if I go to my previous slide, alpha 2 is not given, so we can calculate alpha 2. So, we can calculate alpha 2, and alpha 2, therefore, it will be 25.9 divided by U2 is equal to 59.7 minus Cz2 cot 60 degree. So, alpha 2 will be tan inverse of that, tan inverse of this quantity. Anyway, so this is absolute flow angle at the outlet, but what would be the C theta 2? So, knowing the value of alpha 2, we can calculate C theta 2, because C theta 2 we have already if we can calculate alpha 2, then we can calculate C theta 2, that's then C theta 2 will be how much? C theta 2 by, so if we calculate alpha 2, I can go to the next slide. Then C theta 2 by Cz2 is equal to how much? From the outlet velocity triangle, C theta 2 by Cz2 is equal to tan alpha 2. C theta 2 by Cz2 is equal to cot alpha 2. So, that will be equal to cot alpha 2, and from there we can calculate C theta 2 is equal to Cz2 into cot alpha 2, where alpha 2 we have calculated from the previous calculations. So, now we can calculate what would be the value of, and if we calculate C theta 2, it will be 44.6 meter per second. So, now torque, that will be, now torque will be m dot into mean diameter, mean radius into C theta 2 minus C theta 1. So, m dot is equal to rho into cube into Rm is equal to 0.95 by 2 into C theta 2 is 44.6 minus C theta 1 is 15. So, if we calculate, where rho is equal to 1.2 and q is equal to 11.6, and if we calculate it, it will be around 201 Newton meter, and power P will be torque into omega, that equal to twice 0.1 into twice pi n by 60, where n is equal to 1200, and it will give 25.3 kilowatt. So, this is the answer of this solution. So, with this probably we have understood how we need to solve the problem for an axial flow machines. So, essentially what you have to calculate for the key is for axial flow machine, flow area at the inlet and outlet are equal, which will give that flow velocity at the inlet and outlet are equal, and from the given data we have to calculate different component of velocities, right, component of absolute velocity in the tangential direction at the inlet and outlet, component of relative velocity at the tangential direction at the inlet and outlet. From there we can calculate all other quantities, and we have solved the problem. With this I stop here, and we will continue in the next lecture. Thank you.